Hi everyone, this week we'll be discussing Victor's tutorial, right? So this week's tutorial is based on special purpose op-amp circuits, right? So let's start off with this week's tutorial. Uh, question number one. Question number one is to determine the voltage gains of op-amps A1 and A2 for instrumentation amplifier configuration in figure 1453, right? So basically we are talking about this particular figure, right? So we need to find the gains for op-amp A1, right? This particular circuit, and op-amp A2, right? So if you see closely, this particular op-amp circuit, right? This from here, here, and here is a non-inverting amplifier, right? And if you see A2, again it is a non-inverting amplifier. So the gains for A1 and A2 are given by 1 plus R1 upon RG. That's the gain for A1, right? That would be 1 plus R1 upon RG. The gain for A2 is given by 1 plus R2 upon RG, right? So the values are already given, right? So what we need to do is to directly substitute the values to get your gains. So gain for op-amp A1 is given by 1 plus R1 upon RG, right? So you know the values of R1. R1 is 100 kilo ohms and your RG is 1 kilo ohm. So if you substitute the values, you'll be getting 1 plus 100 kilo ohms upon 1 kilo ohm, which is equal to 101. So the gain for op-amp 1 is 101. The gain for op-amp 2, right? The gain for op-amp 2 is given by 1 plus R2 upon RG, right? Which is, again, you know the values of R2 and RG, right? So if you substitute the values directly, so you can see that you get 1 plus 100 kilo ohms upon 1 kilo ohms, right? So the final gain for op-amp A2 is equal to 101, right? So moving on to question number 2, right? Question number 2, we need to find the overall voltage gain of the instrumentation amplifier in figure 1453, right? Again we are talking about the same figure, right? So we just need to identify the overall gain for this particular amplifier. So the overall gain for a instrumentation amplifier is given by 1 plus 2R, right? So 1 plus 2R upon RG, right? So the R, right? So the overall closed loop gain for this particular instrumentation circuit is given by 1 plus 2R upon RG, right? So this R means this R is equal to R1, which is equal to R2, right? So if you directly substitute the values, right? So you get 1 plus 2 times the R value, which is equivalent to R1 and R2, right? So which is 100 kilo ohms. So if you substitute 2 times 100 kilo ohms upon RG, which is equal to 1 kilo ohms, right? And if you simplify that, you'll be getting 1 plus 200 kilo ohms, right? That is 2 times 100 kilo ohms, right? You'll be getting 200 kilo ohms upon 1 kilo ohms, right? So the overall closed loop gain for this particular instrumentation amplifier is given as 201, right? So that's the overall closed loop gain for this instrumentation amplifier. Moving on to question number 3. Again, it is based on the same figure. We need to find the question states that the following voltages are applied to the instrumentation amplifier in figure 1453, right? So V in 1 is equal to 5 millivolts, V in 2 is equal to 10 millivolts, and voltage common mode is equal to 225 millivolts. So we need to determine the final output voltage. So the final output voltage is given by the overall closed loop gain multiplied by the difference in the input, right? So if you do that, so your final output voltage is given by the overall closed loop gain multiplied by the difference in input voltage. So that would be V in 2 minus V in 1, right? So which is equal to your closed loop gain we identified from the earlier question, that is 201, right? Remember from question number 2, which is given by 1 plus 2R upon RG, right? So you know your closed loop gain, which is 201, and you know your V in 2, which is equal to 10 millivolts, and you know your V in 1, which is equal to 5 millivolts. So if you directly substitute the values, right, so you'll be getting your V out. So your V out, the final output voltage, right, is 1.005 volt, right. Moving on to question number 4. For question number 4, what value of Rg must be used to change the gain of the instrumentation amplifier in figure 1453 to 1000, right? So what that means is we need to now change the value of Rg to get the overall gain as equal to 1000, right? So we need a gain of 1000. So in this particular case, what it means that your Rg value is unknown, right? So your closed loop gain is given by 1 plus 2R upon Rg, right? So if you see, your overall gain is given by, the overall closed loop gain is given by 1 plus 2R upon Rg, right? So what you need your overall gain as 1000, right? And you need to identify your Rg. You know your R, which is equal to R1, which is equal to R2. So it is 100 kilo ohms. So now what we need to do is to rearrange the formula, right? We need to rearrange this particular formula and make Rg the subject of the formula. So if we rearrange this particular formula, we get 2R upon overall closed loop gain minus 1, right? So you know your R value, which is equal to R1, which is equal to R2, right? So R1 and R2 are equal. So which is 100 kilo ohms, right? So 2 times 100 kilo ohms upon your closed loop gain, that needs to be 1000, right? So if you need to substitute that, minus 1, right? So you'll be getting 200 kilo ohms upon 999, so which is equal to 200.2 ohms, which is approximately equal to 200 ohms. So your Rg needs to be approximately equal to 200 ohms, right? So that's the solution for question number 4. Moving on to the last question, which is question number 29. For this particular circuit, right, this is a logarithmic amplifier, right? So we need to so the question reads, signal compression is one application of logarithmic amplifiers, right? Suppose an audio signal with a maximum voltage of 1 volt and a minimum voltage of 100 millivolt is applied to the log amplifier in figure 1460. What will be the maximum and the minimum output voltage? What conclusion can you draw from this result, right? So what we need to do is we know that V out will be given by negative 0.025 volt ln into V in upon IEBO into R in, right? So this is the formula for your output voltage, right? This is the formula that we need to use, right, to get our output voltage. So first we need to identify the maximum output voltage. So you'll be using the maximum voltage, that is 1 volt, as your V in, right? Your IEBO, right, which is given as 60 nanoamps, right? And that is your emitter to base operation, your emitter to base current, right? So that is 60 nanoamps, right? So your R in, right? So your R in value is equal to 47, right? So it is, the R in value is already given. It is 47 kilo ohms, right? So directly substituting the values, right, you'll be getting the maximum voltage, the maximum output voltage is negative 147 millivolt, right? To get your V out minimum, you need to use the minimum input voltage, right? That it's 100 millivolt, right? Your IEBO will remain same, your RE value will remain same again. So directly substituting the values, your minimum output voltage is equal to negative 89.2 millivolt, right? So what conclusion can you draw from this result? The conclusion that we can draw from this particular output voltages is that the signal compression allows larger signals to be reduced without causing smaller amplitudes to be lost, right? in this case the 1 volt peak is reduced by 85%, but 100 millivolt is reduced by 10%, right? So that means the signal compression in larger voltages, right? So in your maximum output voltage, right, is by you reduce your input voltage 1 volt, you compress it by 85%, right? And you compress the minimum voltage 100 millivolt by 10%. So the compression in larger signals are large, right? While there is a small reduction in smaller voltages, right? So that's it for this week's tutorial. If you have any other questions related to this week's tutorial, you can drop an email to any of us in the teaching team, right? So with that, we end this week's tutorial. Thank you.